science and engineering, and you all have seen his lectures from week 3 to week 6, where he has covered linear algebra concepts. So now we are in week 8 and end of week 7. So sir, all your lectures have completed for these students.
Oh, okay, great. Yeah.
And there have been a lot of questions regarding many concepts. So they wanted to interact with you, and it's a great opportunity for all of us to interact with you. So, sir, can we open the question forum for students now? Or you want to say?
No, I don't want to say anything. I think we'll just take the questions as they come and keep the discussion dynamic. I don't think there's any set agenda. Yeah.
Okay, okay. Yeah. So anyone who wants to ask any question, please raise your hand or type in inbox so that we can allow you to speak.
Yeah, if you can let people ask questions one by one in some order, it would be great.
Yes, sir. So anyone who is having any doubt, please raise your hand.
Yeah, you can feel free to ask any question. Is fine. I think last time we had a useful interactions session where we had to cut it at 2 hours because it became excessively interactive.
Yes, sir.
So this time we have a silent bunch. How many are attending?
So it's 48 now. So it's a good number.
Yeah, ask questions. Yeah, some concept is not clear, if some motivation is not clear.
Yeah, so sir, Steve Richards has raised his hand. Yeah, you can unmute and ask.
Sir, I watched the lectures. I'm having a hard time understanding the singular value decomposition. Can you just, walk me through the steps of solving one of those sums?
Okay, so let's see. I have to find the notes somewhere. Just hang on. Let me find the notes and then see. Should have something somewhere. This is eigenvalues. Okay, just give me a couple of seconds. I'm just trying to locate that school. Okay, I found something. Okay, let me share my screen. Share screen. Are you able to see my screen now?
Yes, sir.
Yes, sir. It is clear.
Okay, so if you recall singular value decomposition, I'll just take the result somewhere. So the point is, if okay, the question now I have is when can you diagonalize a real matrix? Can any real matrix be diagonalized, a square matrix?
No, sir.
Okay, so what's the result before SVD that we saw? What's the class of matrices that can be diagonalized?
For for a square matrix, it must be symmetrical, and if it is complex, then it should be Hermitian.
Yeah, it should be Hermitian. Okay, so the important thing is, yes, real symmetric matrices and Hermitian matrices are diagonalizable. And if you take any real matrix, it's not necessarily diagonalizable. But an alternative is to go through what is called as a singular value decomposition. So I can take any real matrix, need not be square, even rectangular, and I can write it out into a product like this. It's a decomposition. There are several matrix decompositions. SVD is one of the popular ones. So I can write it as, a product of two orthogonal matrices and a diagonal matrix. These orthogonal matrices Q1 and Q2 are in different dimensions. Because I'm decomposing a M cross N matrix, Q1 is M cross M, Q2 is N cross N. And this diagonal matrix sigma in the middle will have the singular values. Okay. So whoever asked the question, is this decomposition statement clear?
Yes, sir. So far clear.
So far clear. Now what goes into Q1? Anyone can answer. As a relation. So I mean,
Sir, vector, sir,
eigenvectors of
eigenvectors.
Q1.
Eigenvectors, sir.
Correct. Of which matrix?
A transpose A.
Eigenvector. Yes, sir.
Okay.
A transpose A.
And what about Q2?
A transpose.
Okay, let's verify that. I think it should be in the end. I remember having a note somewhere. So AA transpose, you see, just the opposite. I believe you said the opposite. Yeah.
Yes, sir. A transpose A must be a scalar value.
No, A transpose A is not a scalar. It's a different matrix. Look at this. Same. The question is whether AA transpose is M cross M or N cross N. A is M cross N. What is AA transpose? What is the dimension? Is it M cross N or M cross M or
M cross M.
M cross M.
M cross M. Okay. All right. So the point is when I write it down, if I look at A, right? If I do A into A transpose, in the middle I'll get something. So why is A into A transpose like this? Because the one in the middle vanished because Q2 is a orthogonal matrix. Is that much clear?
Yes, sir.
Okay, so somewhere okay. Okay, my Apple Pencil has gone out of battery. Okay, let's see. So the point now is A transpose. So the point is if somebody says that A can be written as Q1 Q sigma Q2 transpose, if he already gives you that, then it's easy to infer that Q1 will have the eigenvectors of A transpose and Q2 will have the eigenvectors of A transpose A. All right. Okay. Now that much is clear. Now the question I have is, this is just a simple question. If I look at the eigenvalues of A transpose and A transpose A, I will not prove this, but I just want to ask, will they be the same or different? This is a homework problem. This you can go back and check. Will they have the same eigenvalues, not vectors? Vectors will obviously be different because they are in different dimensions. But what about eigenvalues?
Sir, they'll be different actually.
They'll be different. You may want to recheck that. Okay.
Okay.
Yeah. So the point is okay. Now the other thing is now I want to find. So what goes in sigma is the square root of eigenvalues of A transpose A. That's the proof here. So the point is A transpose. If I look. I mean, I'm not going to go through the entire proof, but what you do is, if I look at A transpose A, that's a diagonalizable matrix. Why is it a diagonalizable matrix? Why is A transpose, even if A is rectangular, A transpose A is
it's real and symmetric because
it's real. Yeah, so that's it. So now I can take the eigenvalues of this and take the square root of that eigenvalues. And those positive eigenvalues I call the singular values. Okay.
why do we take the square root, sir?
Why do I take the square root is actually part of this proof actually. Yeah. Okay. So I'll have to go through the proof. I mean, this proof I remember doing. Did I do this proof in the lecture?
Yes, sir, it was there.
Yes, sir.
Yeah, we could go through the proof. If people are interested, I can go through this proof, but it will take some time.
I actually don't recall why it should be.
Okay, so the point is, okay, how I do this is, okay, the proof, I mean, very quickly, I'll jump over the details, but I'll very quickly tell you the proof. A transpose A is diagonalizable, right?
Yes, sir.
And what is the dimension of A transpose A? It's like, what size matrix is it?
N into N.
N cross
N
M.
into N. So
Cross
if
M.
it is diagonalizable, if you remember from whatever I taught in this course, then I'll get N linearly independent eigenvectors. Is that clear?
Yes, sir.
Yes.
And if I get N linearly independent eigenvectors, I can definitely make them orthonormal. Okay, something that was not taught in this course. If I give you N linearly independent eigenvectors, what would be the algorithm or procedure that you use to make it orthonormal?
Graham-Schmidt process.
Graham-Schmidt. Yeah.
Graham-Schmidt. So you know that. Okay, so I call this x1 to xn are these orthonormal eigenvectors with corresponding eigenvalues lambda 1 to lambda n. These are not necessarily distinct, but there are n eigenvalues. Okay, and the point now is okay, now you'll be able to see my cursor. So the point is these lambdas, these xi's are orthonormal, which just means that it is of length n, length 1, and you know they are ortho. This is the orthogonal part. Okay, this is the orthogonal part. This is the normal part. Okay, and now what I do, if I quickly show is, so the point is after this, the next thing that I show is, see the point is I take square root of this eigenvalues. Now, can lambda be negative?
No, sir.
Oh, no, sir.
No,
It
sir,
cannot
no.
be negative, and that's this passage. I'm not going to do the proof, but it shows, I mean, this passage shows that lambda is greater than equal to 0. All right. The next stop is I'm going to take the square root. See, I'm trying to, I mean, very briefly, the point is if you're looking at eigenvalues of lambda, but you're trying to write down a decomposition of A. Okay, the eigenvalue lambda is of A transpose A. So you cannot just put the eigenvalues as it is in the diagonal and hope that this decomposition works. So the intuition is that, okay, you need to do something because A transpose A's eigenvalues should not directly figure as it is. I mean, do you expect, imagine I take a matrix, I square that matrix, look at the, I mean, very brief, imagine I take a diagonalizable matrix. All right, if I take a diagonalizable matrix, I'll write something here. Imagine I can write some A equals Q sigma Q T Q transpose. Okay, so if I look at A square, what will be the decomposition?
Q D square.
D square.
Transport.
Right. So the point is, when I go from A to A square, what happened to this diagonal entries?
It will be squared.
It will be squared. So the point is, when I'm looking at eigenvalues, this is a very loose, high-level argument why I took the square root. The rigorous proof is whatever is covered in the class, in the lecture. But the point is here, this is a matrix for A. You take away these orthogonal matrices, this houses something that should be related to the eigenvalues of A at the level of A. So you cannot just put the A transpose A's eigenvalues here. So square root is one way it makes sense, and square root makes sense also because of this proof. The square root would make sense because of this proof. I mean, this proof is a little elaborate, but if you follow the logic from here, you take these square roots and then you get R of them. Imagine you get R such positive eigenvalues and the rest are all 0. So we argued that all the eigenvalues are non-negative, but some of them will be positive, the others will be 0. So you take these ones and you define these yi's, put them in a matrix, you extend them to a basis. You may not get m vectors. Here. You will get only R of them. See, these yi's will be R of them. So you want a basis for Rm. So you extend it. To a basis. Call them y1 to im. Put them in this matrix, and that will be Q1. You write down Q2 as the eigenvectors of A transpose A. This you got already. If you started here, right? This is what you started with. You took A transpose A, you diagonalized it, looked at the orthonormal basis. This is what you got. Okay. Now, the story is that when I do Q1 transpose A Q2, then I'll get a diagonal matrix with the singular values. That's really the story. That's where I get the sigmas. That's where the square root comes from. Okay.
Okay.
So this logic, I mean, you can look through the steps, but what I did was I looked at the eigen vectors of A transpose A and put them in Q2 as columns. Okay, stack them up as columns, and I looked at these y.
Sir, you are not audible, sir.
I think we have some technical issue here.
Okay, for some reason I got disconnected. Am I audible now?
Yeah, sir. You are now audible.
What internet connection I'm using? Just I'm using this. There is cover. Yeah, are you able to see my screen?
Yes, sir.
Okay, I don't know. When did I'm not sure when I got dropped off. Can
Sir,
somebody
when-
tell me when?
Yeah, so sir, when you were explaining where we take these columns for y.
Oh God,
Okay,
I
so-
spoke for more than a few minutes and now I have to tell the same thing again. Okay. All right. Okay, so what point is this? Okay, so is Q1 composition clear? How I got Q1?
Sir, screen is not visible.
Okay, wait, I'll share screen again. Only the host can share in this meeting, it says.
Okay, sir. Maybe you disconnected. That's why you're not a host. I'll check.
No, it says only the host can share.
Yes, sir. Give me a minute.
No, it still says host can only share. Should I reconnect, disconnect and reconnect? It's not allowing me to share now.
Yeah, sir. Give me a minute. Actually, you got disconnected, so you're not a host anymore. That's it.
Okay, so the idea is okay. Until then, I'll tell orally. So what you did was you defined certain yi's as a function of xi's. Okay, you got this A transpose A's eigenvectors, and you take the R positive eigenvalues and the corresponding eigenvectors. You take a function of them. Those are yi's. So you get only R of them, and then you extend it to a basis, full basis for Rm. So those are y1 to ym. Okay, is that construction of y1 to ym clear? Am I
Yes,
in this call? Hello? Okay. Yeah, periodically, please just no, don't nod your head, just say yes, sir, or something like that. Yeah. Because it's hard to know when some disconnection is happening. It's good to have active feedback. Yeah, so this matrix that I make up Q1 and Q2, I have already taken, I've already got those n eigenvectors for A transpose A. I'll put them in Q2. Q1 composition is a little tricky. I can only, I have, the special way of constructing these. And now if I look at Q1 transpose A Q2, that will turn out to be a diagonal, that will turn out to be the sigma with a bunch of singular values and then only zeros. Okay, bunch of singular values in a diagonal form, sigma onto sigma r, and then zeros elsewhere. That is that matrix sigma. Okay, so that can be shown. The proof went through that way. No, it still says only the host can share now. You want me to disconnect and reconnect?
Sir, I have a doubt here, sir. The sigma also we are getting from A transpose A, right? Or we are getting the sigmas from A transpose?
Yeah, that's a question you'll have to go back and work. Will the eigenvalues of A transpose and A transpose A be the same or not?
Okay.
If you answer
Okay.
that question,
Okay,
so
sir.
I
Yeah.
won't give you the answer. I won't give
Fine,
you the
sir.
answer.
Fine.
Just
Fine.
figure that. Yeah. See, the eigenvalues, the eigenvectors will obviously be different because A transpose is some M cross M matrix, A transpose A is N cross N. So the eigenvectors live in different spaces. So the eigenvectors, there's no way they can be same. But what about eigenvalues? Yeah, just figure that. Okay?
Yes, same.
But anyway, that sigma is figured out by taking you. I mean, the easiest answer is this. If I don't want to complicate this any further, take A transpose A, write down that matrix, calculate its eigenvalues using the standard like determinant of whatever that A transpose A minus lambda equals 0. Calculate that, you'll get certain eigenvalues, take the square root, that's what it is. Yeah. Okay. So that sigma can be composed like that. Now the question is sigma, what is the size of sigma matrix? Is it a square matrix?
Sir, shall I share your lecture notes till he makes you co-host?
Actually, it would be easier if I had shared because I'm on my iPad. I can highlight stuff and all.
Yeah, okay, sir.
But if you can't make, can't you just change the settings that anyone can share? What is the
So
problem?
actually, sir, we are also co-host. So the host can change that.
Correct. But if you go to the Zoom meeting settings and allow anyone to share, it should be okay, right?
Okay, okay, fine, sir. I'll check.
That's easier. Why should it be that only the host can share? Actually, I think the default setting is probably, I think the default setting is a host can share in Zoom. Whereas you have to go and change the meeting preferences to make it anyone can share. Only the host can do it. Yeah, I still cannot share, but somebody was asking something. Yeah. So I think I clarified about how the sigma matrix is composed. I can't walk you through the example until I share the screen. Until then, we can take other questions instead of just waiting for some log to release. Yeah.
Hello, sir. I had a question about PCA.
Huh.
So when we do PCA, we are basically projecting the data set onto a smaller space. Correct. Yeah. So then.
Yeah. Low dimension space.
Yeah. So then it would be. So these elements in this smaller subset will be a subspace. Will be a linear combination of features in our original data, right? So what would that mean physically when we have a real data set and when we reduce the dimensionality? What would each of these features mean?
Features, coming from, I mean, you collected features which are like really high dimensional, say 1 million.
All right.
Okay, 1 million bits or columns, so that's the dimension. And then you project it onto a space of, a subspace which has dimension 20.
All right.
Yeah, so that just makes the computation a lot simpler, right? If you work with quantities which are in a 20-dimensional space versus quantities which are in, I don't know, 1,000, I mean, anything, bigger numbers.
Yes, obviously. I'm asking from more a practical point of view in the sense that your data has some features and features have physical meaning.
Correct, but there will be redundancy. So the point is, I mean, to save computation, you just work with low dimensional ones to save computation. It's just a dimensionality reduction is purely motivated by computation. Okay, if you are having some MATLAB or Python, try inverting a 10,000 by 10,000 matrix.
Yeah, I know it is very difficult. Like you can't. Yes, I've done that. Tried that. Yeah.
So then, if I give you a matrix in order hundreds or less than 100, then it's all the computation is feasible, fast, all of those.
Yes, my
So
question
you have to
really-
you're reducing features simply to save computation power and gain speed. Both.
Yes, I understand that. My question really is that would the lower dimensional data we created would can we assign a meaning to those 20 features you have right now?
No, that minimizes the reconstruction error. That's how PCA does it. Or maximizes the variance. So those are the two viewpoints I derived in the lecture.
Yes, that's
So
all
the
right.
meaning is that those are the features. Imagine, okay, for example, imagine I have like so many features. If I want to project it into, imagine I have 1,000
all right.
features and I want to project it onto a 20-dimensional space. So which 20-dimensional space are you going to take?
All right. So these are the original features itself, like not like there will be a combination of them or anything like that.
No, the features like x1 to xn are given. Like these are
all right. I think
these are vectors in some 1,000-dimensional space or 10,000 or whatever.
Sir, can you try sharing screen?
Projecting it onto a space which has dimension 20. Okay, the simplest example is take 2D features. Take simplest example, take two-dimensional features, 2 bits, x and y coordinate. And I project everything onto a line.
All right.
I project everything onto a line. Now, which line will you project? You have so many lines to project.
Yes.
Okay. So PCA projects onto a line that minimizes the reconstruction error.
All right.
Sir, you can
already on the line, then there's nothing. If I give you points, like imagine I give you 3 points. I give you 3 points, -1, 0, 0, 0, and 0, 1 or something.
Okay.
And if I ask you to project onto the line, is there something to do really?
No, like I think they're in the same line. They're in the line itself.
Yeah, I mean, okay, I need to imagine 3 points, -1, 0, 0, 0, and 1, 0.
Yeah, they are in a line already.
They are in a line already, but these are still 2-dimensionals, right?
Yes.
Now the point is, if I push these points slightly away from -1, 0, and slightly away from 1, 0, then you'll have some consideration onto. Imagine they are not on a line.
Yes. I understand.
Then you'll have to find the line that minimizes something.
Okay.
That PCA uses is minimizes the reconstruction error.
Yeah, all right. Understood.
Okay, so that's the point. So the point is eventually they're still, I mean, if you look at those points, they'll have still 2 coordinates. But if you look at the subspace, like these 3 points that I gave you, they are in a line.
Yeah.
It's not like you're chopping off coordinates. I hope you don't get confused that way.
Yeah. Okay.
Yeah.
Good afternoon, sir.
Yeah.
Sir, I have a doubt regarding the PCA and the dimensional reduction problem, and I am comparing with the Pareto analysis. Can you do the comparison?
No, that's outside the scope of this course, man. I mean, if you have questions about what I have derived Pareto analysis, I am not. Now I can share screen. Yeah, I can share the screen now. Okay, great. Thanks, Abhinandan. Yeah. So I don't want to cover topics. I'm not even sure what Pareto analysis is.
No, so Pareto says with the 20% of the features, you can derive up to the 80% of the output.
Yeah, but in what sense?
So suppose sales data, I have sales data, and it says out of the 100 products, only 20% products make the 80% of the revenues.
Yeah, but if I just, I mean, there's no revenue or anything, right? I'm talking about PCA where I just want to reduce the dimensionality.
So, sir, ultimately,
so mathematically, can you tell me? I mean, mathematically, can you tell me what this Pareto analysis is?
In my understanding, mathematically, Pareto says if you have 100 features and
100 features, I mean, you 100 like you have feature vectors in dimension 100.
100 products means 100 features of the revenue. Revenue is function of the products, number of the products.
No, your feature is a 100 dimension, 100 bit vector, is it?
No, sir, it's only one dimensional vector, but number is 100.
No, I don't understand. If it's one dimensional, PCA is not even making sense there.
Yeah, sorry, sir. I mean, I think he is asking about 80-20 rule kind of thing, so
yes,
which is in economics. So
yeah, but you have to make it precise in the context of PCA. It's not clear to me. Yeah, see, PCA reduces features. There are 100 feature bits. If the features are all in some 100-dimensional space, say R100, Euclidean space 100, then I could project it onto a space of size 10 also. So where I'll project, that's the reconstruction error. Yeah. So minimize the reconstruction error. So this 80%, 20% rule applied to PCA, you'll have to make it mathematically precise to claim whatever you're trying to claim. So that's the reason why I said it's like really outside the scope of this course.
Okay, sir. Okay, sir. I won't take much time of my friends and yours also, sir. We can discuss more other things.
Correct. Yeah.
Thank you, sir.
Yeah, sure.
Yeah, anyone else? Please raise your hand if you have any doubt. Or you can type in chat box.
Okay, somebody asked me to go through that example. I'll quickly go through that. Okay.
Yeah, sir. Okay.
Now are you able to see my screen?
Yes, sir.
Okay, so the point I was trying to make earlier was you make these vectors y1 through yr come this way. They are directly defined using exercise. So you have R positive eigenvalues of A transpose A, R of them in some number R, which you don't know. Okay, so you take this R of them and you define yi's like this, where sigma is square root of lambda I. This square root makes sense because these lambda i's are all positive, strictly positive, not zero. So for them, the square root makes sense. So I take this, I define it like this. I take these yi's, I extend these yi's, there are R of them to a basis. And this y1 to ym, which will be a basis for Rm, will be put in a matrix as columns like this. And in Q2, I put the eigenvectors, which I already found in the very first step. A transpose A, I diagonalized. So this orthonormal set of vectors, I put x1 through xn. Now, if I do Q1 transpose A Q2, and if you follow the logic here, then this will turn out to be a matrix like sigma with all these bunch of stuff, singular values and zeros elsewhere. Now, this question, very basic question I have to students is this sigma a square matrix? Always? Is sigma a square matrix?
Yes, sir. Yes, sir.
Yes, sir.
Okay, so I have Q1 sigma Q2 transpose, say. This is M cross M. This is N cross N. Now tell me what is the size of sigma?
M cross N.
Then why is it square?
Sorry.
Okay, so this is not a square matrix. Please recognize it. When you try to work it out, if you get a square matrix, if you start with if M equals N, yes, it will be a square matrix. But if M is not equal to N, if it's a proper rectangular matrix, either wide or tall or one of those, then this is not a square matrix. Okay.
Sir, but why doesn't it have to be a square matrix? Because these sigma values are essentially coming from a symmetric matrix, and the symmetric matrix will have like
Just hang on. A is M cross E. A is not necessarily square. Any M cross N matrix, A is a M cross N matrix, where M is the number of rows, N is the number of columns, and they are not necessarily the same.
But these sigma values would be from a symmetric matrix, like the square root of the eigenvalue.
Yes. This part, sigma values go in the diagonal part of this, but there are a bunch of zeros here. These zeros are like matrix zeros. Okay. These are not just single zeros. These are like a bunch of columns and rows. So take an M cross N matrix. This is R cross R, and make it a M cross N by throwing zeros elsewhere.
Are these zeros for like the eigen vectors which are in the null space?
No, the point is, yeah, so those we can get into, but I'm just telling about the composition of sigma. The way I write sigma is like this. There's nothing about null space. Sigma is just a matrix with either eigen, the singular values or zeros. There are no vectors in this really. The eigenvectors of A transpose will go into Q1. The eigenvectors of A transpose A will go into Q2. And sigma will just house some numbers, which are these, given by exactly this. You make up a R cross F. So this is, so you can write it like this. This is R cross R, this part. Okay. And then this whole thing is M cross N. So you need to adjust the rest of the zeros. You can write it down. I don't want to write it. Yeah. Okay. So this 0 is like a 0 matrix with some number of rows and some number of columns. Okay. So how many rows? Can you tell me the dimension of this? Somebody can tell this. This second 0, this 0. M minus R
M
times
minus R.
Okay. Similarly, fill the rest. Yeah. So similarly, fill the rest of the dimensions. So the point is, this will be a rectangular matrix if A is rectangular. If A is square, then sigma is square. Okay. Yeah. So I was trying to go through now. Yeah.
So is there any relation between
somebody
Q1
has a
and
question?
Q2? Yes, sir. Sir, is there any relation between Q1
No, I mean,
and Q2 with the?
There's no, I mean, what do you want as relation? Q1 houses eigenvectors of A transpose and Q2 houses eigenvectors of A transpose A. These are two different matrices in two different dimensions. Q1 is M cross M and this is N cross N. So,
no, sir, I'm asking that is there a relation with the fundamental subspaces, like Q1 is null space of Q2 or something like that?
Oh, for that you can look at. There is a relation. Yes, if you want that, you'll have to go through Gilbert's time. Yeah, let me show that. It should be there somewhere. I need to look at Gilbert's time yesterday. Where does it talk about SVD? It's there at the beginning of where it does SVD. Where 367. Eight, 200. Somewhere nearby. Okay. Do you see the remark too? This is something that you can figure. The Q1 and Q2 are U and V here.
Okay, okay, sir.
Yeah. Okay, so this is something that you can figure. Okay. Yeah, let me go back to this note. What I was trying to say here was, if you want to look at a simple example, take this example. A transpose A. If you want to go through step by step, calculate the eigenvalues, take the square roots, and sigma is, why is sigma a square matrix here? Because A transpose, I mean, because A itself was starting, with this. A is here. Okay. A is here. So A itself was square, so sigma is square. Now the point is, what should I do next? I have to find the eigenvectors of A transpose A and put them in Q2. So finding eigenvectors, I have given this matrix. A transpose A is this matrix. So I hope you know by now how to calculate the eigenvectors, which is write down this and then find the eigenvectors. Okay, x1 and x2. Okay, so which is coming from a certain null space and all that. And then so you get Q2, and then you can use. So the point is, this relation can be easily used. If you remember the definition of y1 and y2, because it is square, you can just use this definition and directly write out y1 and y2. If you remember how y1 and y2 was formed, ax1 divided by sigma 1, ax2 divided by sigma 2. This is one way. The other way is go and calculate the eigenvectors of A into A transpose. But the point is, this is shorter because you know sigma 1, you have already calculated x1 and x2. So this is actually a lot more easier to do than the other way. Okay. So I get Q1 directly. And then I write A equals Q1 sigma Q2 transpose. Okay. This 1 by square root 3, all of this is to normalize. Okay. So you need, the important bit I have to tell you is, after you find the eigenvectors, you need to normalize them. Okay. All right. Is this passage clear? Why this equation is because that's how we constructed. That's the reason why this proof is important. If you go back to the proof, here, that's where we started. If you remember this yi's, we defined R cross R. So the point is here, the reason why, I mean, okay, imagine hypothetically that, there are no zero eigenvalues, which was the case that I had for 2 cross 2. Then what will this matrix Q1 have? So the question now I have is, if there are no zero eigenvalues, if all the eigenvalues of A transpose are strictly greater than 0, then do I have to do this basis extension? Hello?
Yes, sir, you're audible.
Yeah, guy, I mean, folks, please let me know, because I'm not sure when I've dropped off, because I'm in a different application context. So when did you do this extension to basis? You define this R of them here, Y1 through YR, and then you extend it to the basis under what situation? Did you do it always? Do you have to do it always? Can you tell me one example where you don't have to do it?
Sir, when we have enough
matrices.
No, I mean, if I have all positive eigenvalues, do I have to do this extension to basis? If sorry, yes.
There's no need of doing that.
There's no need. That was the example that I had. You remember there were 2 eigenvalues, 4 and 1. So they were both positive. So all I have to do is I have to calculate Y1 and Y2 and I'll get the Q1 matrix. Do you understand? Do you understand why this? See, the point is,
can you explain
first thing to do is calculate
Yes, sir,
A
please,
transpose.
again, sir.
Yeah. So the point is, if all the eigenvalues, imagine all the eigenvalues, say lambda 1 until lambda 1 are greater than 0, then how many yi's do I get here? So I'm writing in right here, if lambda 1 to lambda
Equal to n, equal to n
all
you will
greater
get.
than 0, then I get y1 to yn directly using this formula, using star. I call this star. Right? I'll get this, right?
Yes, sir.
Yes, sir.
Yes,
One
sir.
n vectors, I just put them in this matrix Q1. I already got n eigenvectors. I don't have to do any basis extension. The extension has to happen only if there is a zero eigenvalue. Only if there is a zero eigenvalue, you have all this mess of extension and business like that. Otherwise, it's straightforward. And the point is, why is this computation easy as compared to computing the eigenvalue of A transpose? Simply because Xi is already computed. To calculate Q2, the matrix Q2 is X1 to Xn. These Xi's are all eigenvectors of A transpose A. And this is something that you anyway have calculated. So you have all the Xi's. You have them with you. By the time you come here, you have the Xi's. So this is a very straightforward computation. You just apply A to this eigenvector and scale it appropriately with a singular value. So this is what you do, yi. So this is a lot easier to compute than going and computing all the eigenvectors of A into A transpose, which is a lot more calculation. So A into A transpose is another matrix, and then you find its eigenvalues, okay, but you have to find its eigenvectors, which is a lot more work than just doing this assignment like this. Do you understand the point?
Yes, sir.
Yes, sir.
Okay, so the point, that's what I want. That's the point I wanted to make. So in this particular example, when I did this, I got eigenvalues all positive. There was not a single zero. So all I have to do to calculate Q1 is just write out these two, write these, and I get y1 and y2. That's all there is to it. So this is an example which is a lot easier than an example where there is if A transpose A had 0 eigenvalue, then you'll have to do a little more work. Okay. All right.
So yes, sir. Just another question. I'm sorry, this may be rather stupid question, but
it's okay. Everything is stupid. The moment you ask, it's fine.
Right, sir. So this, when we get one eigenvalue as 0, you said we need to extend the basis. Okay, so I didn't exactly.
No, but I want to do that. I'll tell you what you can do to find Q2. What is the alternative? What goes into Q2 by this remark? Do you see this?
Yes, sir. Yeah.
So you can calculate, not Q2, sorry, Q1 is what you're talking about. So in Q1, you just have to put the eigenvectors of A transpose.
Okay.
That you can calculate directly also.
Okay.
So there's no need of basis extension, any of this business. So you will have to use, you'll have to be clever. If you see that there are no 0 eigenvalues, then you have a simple enough formula to get you all this Q1. Okay.
Right.
But if there are 0 ones, then just write down A into A transpose, find its eigenvectors. You'll get it, put them in Q1.
Right. Thank you, sir.
And make sure when you multiply, I'll tell you in exams or even in real life, wherever you do this, make sure finally, like this is something I've written here. After writing all this Q1, Q2, a basic sanity check is this. If this does not work, then you have made a numerical mistake.
Right.
In the end, I have taught this course multiple times in the traditional sense also. People get even the dimension of this wrong. So this has to be M cross M, this is M cross N, and this is N cross N. Now if you give me a matrix which is, it does not even allow this decomposition, which does not make sense, then it's a loss, I will tell you. So make sure you get, the first sanity check is to get these dimensions right. And then final sanity check is to check your answer by doing this product. Yeah.
Right.
Yeah. So that's a sanity check that you can do. Yeah.
Yeah. So, sir, there is a question from Vivek. So, can you unmute Vivek Bajaj?
Yeah, I'll stop sharing. Maybe let's see if it's needed. I'll share again.
I think I can unmute myself.
Yeah. So you can ask your question.
So, sir, this, it was just an extension of the question asked by the previous person, a fellow student. So my example is very clear that I have to, find the house prices of, say, it's a practical thing. I need to find the house prices for the purpose of valuation. And there are, say, 20 features in that. And I fitted a linear regression. But those 20 features don't make sense because the coefficients are very, very small. And so I want to reduce the number of features. So my question one is, can I use PCA to find which are, reduce them and find which are the important features for prediction of house prices?
The 20 is already small.
Oh, not for practical purposes.
Already small. You can work with 20 cross, you can work with 20 cross 20 matrices, right? It's very easy.
Yes. Sir.
So a question for, if the PCA won't change the quality of features.
Okay.
If you are given 20 features, 20-dimensional ones,
right, sir,
then you just work with that. You can't get any better with PCA. You can only get worse.
Okay.
So if your performance with 20 features is not good, then PCA will not make it better by dimensionality reduction.
Right. So actually the interpretability, because some of the features, the coefficients are so small, that does not make sense. So I thought, if for practical point of view, we know which are the 4 most important features which can affect the evaluation. So in that sense,
could be based on domain expertise. But my point is, I'll tell you the motivation for PCA is exactly what I was saying before. If the dimension, you have to work with D cross D size matrices, like where D is the dimension of the features. And if that D is large, then it's very difficult. Like 10,000 features. Imagine you have 10,000 bits.
Okay,
like
right.
columns. You have a vector of size, 10,000
Right. So
dimensional Euclidean space. Then, all matrix computations will be time consuming.
Right.
So in that case, reducing makes sense.
Right.
But 20 is already small. Honestly,
Small.
20 is small. Yeah.
So will there be a problem if the number of features say 10,000 and the data is less than 10,000?
No, that's a canonical setting, right? For PCA, I mean, you have less number of points. If you have data in high dimensions, but the number of samples is smaller.
Smaller, right?
Yeah, then I tackled that in the course. PCA in higher dimensions. That's where the SVD trick.
Okay. Right. Okay.
So then, see, the point is then instead of working with D cross D, see, if you look at all this D-dimensional features and all that, right? When you do A transpose A transpose, all of that. So the question now is, if you look at the PCA in higher dimension discussion, imagine N is the number of samples in the data.
Right.
D is the feature dimension. Then there is a way of working with only matrices of size N cross N and not D cross D.
Right. So I remember you taught that. Right.
Yeah, that trick works. That's exactly the setting that you're talking about. You have large number of features and a small number of data points.
Right.
But if it's the reverse, then do the normal PCA because D cross D is smaller than N cross N.
Okay. Right.
Yeah.
Thank you.
So, sir, Parth had some question. Parth, you may go ahead.
Yeah, I just need a water break, man.
Yeah, okay, sir. Sure.
Okay, I'm back. On to the next question.
Yeah, so Parth, you may unmute yourself and ask question.
Sir, I wanted to ask, what is geometrically so special about symmetric matrices that their eigenvectors are always orthogonal?
No, I don't understand. Geometrically, no, honestly, I don't have a good answer to that. I don't have a geometric answer to why the real symmetric matrices are diagonalizable. Yeah. Proof is there, but Why is it geometrically? No, I don't have a geometric interpretation to why symmetric matrices.
Is it like, do symmetric matrices project like the space along a line or something, like reflect?
No, there are no projections involved, right? It's just a matrix.
Oh, I mean, like transform.
Yeah, but where is the line? There's no line. Yeah, I don't know if there is a way to interpret that matrix as a. I don't think so. I'm not come across this. The point about that. So the point is okay. So the other thing to note is real symmetric matrices are not the only matrices that are diagonalizable. You could have matrices that are not symmetric but still diagonalizable. I think I have an example of such a matrix in the class notes. So, but real symmetric matrices are diagonalizable. The diagonalizability, the interpretation is that you get enough eigenvectors. If you get, if you have an n cross n matrix and if you can get n linearly independent eigenvectors, then it is diagonalizable. That's where the story is. But a geometric interpretation of real symmetric matrices, honestly, I don't know. Yeah. I can give you geometric interpretation about concepts like positive definiteness or SVD, but real symmetric matrix is just a real symmetric matrix. So I don't know. I mean, there's a way to geometrically motivate anything there. Yeah. I don't know. Yeah.
Okay, sir.
The question of positive definiteness or things like that. I mean, projections, least squares, these things can be geometrically explained. I mean, projections are there, least squares project perpendicularly. I mean, when you solve linear system of equations, I mean, it's like you're looking at an intersection of planes, like something like that. Okay. Each equation can be thought of as a plane and then you want to intersect them. So you want that point where it intersects. Imagine you intersect a bunch of planes, then that intersection point is what you're looking at. That's the geometry for you. Projections have geometric interpretation clearly. I mean, the class lectures have shown that these squares are geometrically interpretable. So is positive definiteness and maybe SVD also. And these orthogonal matrices are also not length changing. If you look at an orthogonal matrix, I said that they don't change the length.
Yeah, it's a rotation.
They can only rotate, but they won't change the length. So those things can be understood. But at a very high level, real symmetric matrices, I don't know. Maybe there is something I'm not aware of. Yeah. I hope that didn't answer your question, but that's where I can leave. Yeah.
So any other doubt, please go ahead and ask the question. Take this opportunity. Sir, we have 100. Yeah, go ahead.
Sir, I have a very basic question that can you explain the sequence wise, like why we need least square and what is the limitation of it? Then we came to SVD and what is the limitation to SVD so that we need to come
So these are
to
different
PCA.
things, right? Least squares, you're just solving a linear system of equations. There is SVD there. You want to solve, I mean, okay, for least squares, let me see if I can find the note somewhere.
Sir, in least square, I have another doubt that by projecting the projection method, we find the least square error. And sir, in the means diagram, that if in 2D, if it is line is 45, means my data is pointed at 45 degree, and I am projecting on the horizontal line, then the error will be the vertical line, isn't it?
I don't know. Without drawing, it's very difficult. But okay, let me dig out my least squares notes.
Yes, sir. Yes, sir.
Should be there somewhere. Oh no, this is okay. This should be. We have these notes, lecture notes. Okay, can somebody tell me which week it is?
Week three, sir. Week three. Sir,
Week
yes.
4.
Week 3, I think. Okay, I
Week
got
3.
screen. Okay, just hang on. Let me share screen. We'll try to find something at least.
So
Are you able to see my screen now?
Yes,
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 sir.
sir, it's visible.
Yes, sir.
Yeah, so this is the least squares business. So if I look at this, right, if B1, so the point is this least squares business, I hope you understand that it makes sense only when the original system is not solvable. And that's when you try to minimize something. And then that's when you project. That's when you project B1, B2, B3 onto the column space of A and stuff like that. Okay. Now on to the question. What is the question that people have? I mean, okay, before least squares, why is it least squares? Okay, I cannot highlight anything here because I'm just looking up from a Google Drive folder. But this E square, whatever is defined here is the square sum of squares. And I'm going to minimize this. That's why it is least squares. I hope it's clear. And I can take the calculus route. I can take the other route. The other route is by just solving, A transpose A X hat equals A transpose B. That system. Instead of solving AX equals B, if I solve that, then that is the projection thing. Now somebody has to repeat the questions. Now I don't know what questions you asked. I don't fully understand your questions.
And sir, one more thing regarding that, that when we have a theta equal b, then it is not coming. But when we multiplying with A transpose, it is coming. So is there any physical interpretation of matrix multiplication that like
the interpretation is that you're projecting it. You're projecting B onto the column space of A. Look at this. That's the interpretation. That's the reason why even if AX equals B is not solvable, A transpose A X hat equals A transpose B is always solvable simply because this, you are projecting B onto the column space of A. That's this system of equations.
Okay, got it.
And that I think is apparent. If you want, I can go through this again, but it's just here. You look at this alternative route. There are two ways I wrote it here. The route is here. See that E vector is that B minus P, I think. Yeah, E is B minus P. And when you project, you minimize this distance. And so, I mean, it's fairly simple. You want to project, so E has to be perpendicular to every column of A. So you write that down. So that's like saying that if I put A1 transpose until AN transpose in a matrix and then multiply B minus AX hat, then I should get 0. That equation is the same as A transpose AX hat equals A transpose B. That's all. So all you're doing through this is A transpose AX hat equals A transpose B. It's not matrix multiplication. It's of course matrix multiplication, but the important point here is that you're projecting. See, the point is if I look AX equals B, if B is already in the column space of A, is AX equals B solvable?
Yes, sir. If in column space of A, then it is solvable.
Correct. But if B is not in the column space of A, I project B onto column space of A and then solve it. And that is the same as writing down, solving this big, equation in the red box.
Okay. Got it, sir. Got it.
Okay. So it's this projection. Yeah. In fact, there are examples. If you look at these notes here, right? If A transpose A, I mean, you'll get back the system if B is already. If you look at B belonging to column space of A, the second note here, then that whole system becomes AX equals B. That's all. I mean, in that case, the projection is totally unnecessary. There's no projection. It's just solving this is the same as solving AX equals B.
Yes, sir. And sir, can you again tell the why when we need the SVD and when we need the PCA?
No, the SVD. Okay, if you want a example where you want SVD, it's just whatever this some other student was giving. Imagine you have high dimensional features. Okay. If you have high dimensional features and if you want to project, then all you can do is you write down, okay, so there should be SVD here in my notability. Okay, I'll just write a random note. Okay, it's maybe better to write something random. Okay, so you have this matrix and you write it as Q1 sigma Q2 transpose, where the sigma matrix is some bunch of singular values and then zeros throughout. Okay, like this, right? Now, what you can do is, if you want to reduce dimensionality, you make up sigma truncated, and then you truncate it to just first some number of values, say sigma 10, and then 0 throughout. You ignore the rest of the singular values, and then you write down A truncated like this. Yeah.
Okay, okay. Okay, so the SVD is actually the dimensionality reduction, right? Hello, sir, I cannot hear you. So is it with only me or?
I can't hear.
Yes.
Yeah.
Okay, I'm really sorry. I
If
don't
it's
know why every time something bad happens with this.
yes, sir, now you are audible.
I'm audible, but again, this host business has come back. Can't share. Abhinandan, you have to do something now.
Yes, sir, you can try now.
Okay, now I can do. Okay, just hang on. I'll just find. Okay, just give me a couple of seconds. I'm trying to find something. In the courses. Okay, I found it, thankfully. So this is SVD motivation. In fact,
Yes, sir. So sir, SVD is just like the dimensionality reduction, right? So these are same.
Look at image compression. Can you see this question?
Yes, sir. Yes, sir.
Okay, so what you can do is you take an image, it will have a bunch of features. Okay, all right, and then you can, when you reconstruct that image, only that with using only the top 10% singular vectors, singular values and vectors. Okay, all right. When you do this reconstruction, at some point, the image is as good as the original one, but using only a small number of singular values. You understand?
Yes, sir.
Okay, so if you have an image, if your features are like what happens in each pixel, okay, then that's high dimensional features. But then you can do SVD and then take only the top 10% and reconstruct the image. And then there are ways to measure output the reconstructed images. You can use what we used here was called the Frobenius norm, but you can do it in different ways. So this is one example where you can do it. I don't have the images here, but you can do this easily. Yeah. You take any image data set and then do this reconstruction. Yeah. That's one way. I mean, if you want more simple example, there is some other example where, you know, if you want to understand this, yeah, do this. For example, if you want to look at the question number 1, just take a 2-dimensional data set. You can do this random in Python. You can generate a random 2-dimensional data set easily. Okay, and then you plot the data set under singular vectors. And now you project this data onto the top singular vector. Okay, the first singular vector, and then see what the reconstruction error is like. Got it?
Okay. Yes, sir. Got it. And sir,
if
now
you do this, you will easily get the geometric interpretation. Yeah.
Okay. Yes, sir. I got it. And sir, now so we can reduce the dimensionality. Then now why we need the PCA? What
No,
it does?
PCA, I mean, the point is this SVD is like this. It's not doing dimensionality reduction. I gave you one example where I'm asking you to project onto the top singular vector. SVD by itself is not reducing the dimension.
Okay, so topmost features we are just selecting.
Yeah, so that's a decision, right? I mean, what I'm trying to tell you is SVD by itself is just a decomposition of the matrix.
Okay, so in SVD we can have loss, but in PCA we will not have loss.
No, the other way. In SVD there's no loss. If I look at SVD, it's just an exact decomposition. A equals this.
Okay.
A equals this, there is no loss. It's just an equivalent way of writing that matrix as a product of 3 matrices where 2 of them are orthogonal and the middle one is having a separate, you know, specific structure. Okay. It's a diagonal matrix, but, you know, having this structure. Okay. Now, what I'm trying to say with SVD is, with PCA is PCA will project, you give me I mean, if you look at PCA somewhere in the notes, I don't know which week it is, probably week 6. Yeah. Given this n data points and an input parameter saying m, which is like the, the dimension of the low dimension of the subspace that you want to project onto, PCA will do such that it minimizes this reconstruction error, this J. Okay, it will find you that space and project onto that so that this reconstruction error is minimized. Okay.
Okay, so here we have the loss.
There is a loss, but in SVD there is no loss because, you know, it's just an equality. You just decompose it that way.
Yes.
Okay, as an example, you can, you know, like whatever I was showing here, as an example, you can project onto top singular vector and do, and see what happens and things like that. Okay. So this kind of things you can do, but more methodical way of doing it is take the PCA route. PCA tells you how to do this. Just write down this matrix, calculate its eigenvalues. Where is that PCA algorithm? Yeah, write down this matrix, calculate its eigenvalues, and then you know how to write down this x tilde. Where is that box? Yeah, do this. X tilde is like this. So these x tilde will reside in an m-dimensional space. Now, if you want the connection of PCA to SVD, that is little intricate, but that is discussed in PCA in higher dimensions. I don't know where I did it. Yeah, PCA in higher dimensions, if you see, here I was telling this to some other student also today. So if you have number of data points which are smaller than the dimension, if you have the features are living in some 10,000 dimensional space, and if you just have 100 data points, then this matrix C, if you look at this matrix C, what is the size of this matrix?
100 by 10,000.
No, just be careful. Is it 100 by 10,000?
Okay, so column vector, so 10,000 by 100.
No, forget that summation and 1 by n. what is the size of xi into xi transpose?
So D cross D.
Yeah, D cross D. And if I sum D, any number of such matrices, it will still remain D cross D, right?
Yes.
Okay, so there's no n. That C matrix is a D cross D matrix. Okay, now if that D is large, but the number of data points is small, then what you can do is you can do a trick like this. This is somewhat motivated by SVD. There is some connection to SVD here. So if I look at A into A transpose, what is the dimension? What is the size of A into A transpose? It is n cross n. Okay, just believe this. A transpose A written like this. That matrix C can be written as A transpose A, where A is like this. But A into A transpose will be n cross n. And that will be like if I have 10 data points, it will be 10 cross 10. And calculating eigenvalues, eigenvectors of a 10 cross 10 matrix is a lot easier than 10,000 by 10,000. So you can achieve PCA by just working with 10 cross 10 size matrix, which is like n cross n, where the n is the number of data points. Okay. So that's
Yes,
really
sir,
now I hope you understand. Okay. Yeah.
Yes, sir. Yes, sir. Thank you.
Okay.
Sir, but
Yeah, go ahead.
like in practical life, are there cases in which the number of features are more than like the data points you have, and we're able to use
Yeah,
this
if you have
PCA?
high dimensional features, yes. You could have high dimensional features, you could collect a lot of information, right?
Yeah.
And then you can get only a small number of samples. Learning in high dimensions is there. I mean, it's obviously practical. Yeah. You can
So
collect a lot of information through features.
So like if we take an example of like IoT data, like maybe weather data, that could be an example, like there are a lot of variables in that.
No, I mean, for example, imagine somebody is coming to our website. Imagine you are going to Google News or something, right? You are going to Google News every day. And Google will have so much information through features about you, right?
Yeah.
Yeah. Do you think it will have just 2 or 3 bits about you? It will have lots of information. Okay. And using that much information, maybe it wants to recommend some news to you. Google News, something. Okay. Now, if the number of bits are like, if it has a million, features about you, then working with that million features is obviously difficult. But then you can do PCA, make it more manageable, bring it down to 100 or 200, and then work on it. Work with that, and then recommend something.
Okay. Yeah.
Okay. So, I mean, for example, I could know where you came from, when did you log in, what you have seen so far. I could make up lots of features. Go your demographics, where you came, I mean, things like that. Okay.
It's like NCR.
And that will be a long vector, like high dimensional vector. And you cannot work with, I mean, after that, you cannot work with that. So if you go, I mean, Yahoo has a website data set like this. You take any recommendation data set, they would have done some dimensionality reduction. They'll give you features which are small. If you take Microsoft Research, also has some data set like this for recommendation, for searching also. Like if like it's a combination. Imagine you put something in a Google search or Bing search box, and then there are lots of results. You want to rank them, things like that. Okay, all of this recommendation business is something that I have looked at in the past. There, the features are usually high dimensional, and the old school way of doing things was to reduce the dimension. Yeah.
Okay, so thanks.
Yeah.
So there is a question regarding a source to study PCA other than Gilbert's rank.
No, PCA, I think you can look at Bishop's book also, but it's a little, whatever I have taught is like an expanded version of Bishop. That's one source. Other than that, PCA Gilbert's rank has a recent book called Learning from Data or something like that. Okay. That also is a good source.
Yeah, okay. Thank you, sir. Any other?
Not the old Gilbert's rank books. He has a book which is like, I'll tell you. Learning from Data, man.
Don't know it's not actually covering that. I took a look. he just explains like Eckhart's.
Learning from data. It's pretty recent, maybe 2 years old or something like that. Yeah. So this has a PCA in one of the units, not the first unit. Like, yeah. By Gilbert-Strang only.
Yeah, please go ahead, ask your questions.
So you had the patience to sit through all those YouTube lectures, is it?
Yes, sir. Sir, I have one doubt.
Ah.
Basically, linear algebra understanding is little bit difficult, and the imagination is also difficult. So for the getting the marks, my strategy is just to solve the practice assignment and the graded assignment, and with that I am able to get the good marks. But if you ask me at the understanding level, then I am not confident. So what should I do?
You need to solve problems. I mean, these not just these problems. Take Gilbert-Strang or any textbook and try solving as many problems. The understanding will come just like that. Yeah. I think for any mathematical course, for best results, I would say solve problems. Irrespective of, I mean, you can look at my PCA derivation 100 times, but if you just solve 10 problems instead of doing that, then your understanding will obviously be better. I'm asking you to solve problems. Yeah. That's the best way, not just linear algebra, probability, optimization, everything. Yeah. You have to solve problems. Yeah. The problems through this course are limited in the sense we cannot check your understanding. Like in a traditional course, I would have questions where I will check your steps, you will write down detailed answers and things like that. But here we are somewhat limited, so we don't have the full power to ask questions. We are still evolving. So through multiple choice and all, there's only a limit on what kind of questions we ask. And we have been trying to be creative, but it's quite challenging. But if you take a traditional course, I can ask you difficult problems where only if you understand, you'll be able to solve. So that kind of problems are there in Gilbert-Strang or any linear algebra book. Yeah, you just solve them.
So that confidence, the inner confidence is not coming. That if even with the confidence, I cannot say that I am a student of IIT and I have learned this. Means even I sigh of telling.
No, that if you solve problems, you will get it. I don't think there's any reason to overthink and overburden yourself.
Okay, sir. Okay.
Thinking cannot solve any of your problems. You just don't, I don't know, I can become philosophical and say, don't worry about your image or something like that. What matters is, there is a way, there's a short way of understanding this subject, which is through problems. So if you solve problems, you will get better understanding. You don't have to worry. Your understanding will not get better by worrying.
Yeah, definitely.
So this, I think the only way, forget marks, the only way solve problems, your understanding will get better. Or read more than Gilbert-Strang, you can read other books. If you want linear algebra, there are lots of books, lots. Yeah, but Gilbert-Strang is the most accessible, but you can go beyond also. There's like the classic text is also, there are many books. There's something by Horn and Johnson. There's something by Karl Mayer. These are good books. But those are like, for me to teach from them, I would require like a full-fledged course. Since this is like one part of machine learning foundations, I'm not gone like a full throttle linear algebra introduction. Yeah. But if you're interested, try solving problems from there.
So final
in Chennai, do you know how it is in Chennai? If without fan, you're gone. Yeah. I don't know where you are. Wherever you are, it's been a while since I experienced cold. Yeah.
Yes, sir. Niranjan has raised his hand. Yeah, go ahead, Niranjan.
Yeah.
Hey, hi, Niranjan, you're on mute.
Hello.
Yeah, go ahead.
Yeah,
sir,
go ahead.
if space is not an inner product space, can we have SVD in that case? SVD and the linear decomposition.
Yeah, that I don't think so. I mean, will you do it?
No.
For
So
SVD, you need the norm, but if that norm is not coming from an inner product, then I don't know, but I don't think so. If you look at the SVD derivation, we are working with inner products and norms. Now, if there is a way to get around that, honestly, I don't know. I don't think so. Yeah. But if you take any Euclidean space, the usual norms come from inner products and the normal complex vector space. So if your features are not like real numbers or complex numbers, but something else, then there is a problem. But with the usual vector spaces, I think it should not be a problem.
So almost all the real data which we are handling in our day-to-day lives have inner product space only.
No, real means it's like the norm is coming from inner product, the natural way.
Thank
you. Real is not the problem, but if you have some arbitrary space where the norm is not coming from a inner product, then it's a problem. In fact, many of the machine learning methods will fail. Like even kernel methods, everything will fail.
Okay.
Yeah.
I wanted to know in real life, all the real life problems can be solved by the inner product space itself. Is there any real life problem where
no, it depends
the
on the
other norms are
features
used?
are not real numbers, but something else. Who knows?
Okay. Okay.
Right now, if you take features as some real numbers, things are okay, but it could be some categorical labels, things like that.
Okay.
I don't know. But these are, I would say, maybe you can still work around them. Yeah. But for this course, at least, I would say it's beyond, but practically there should be enough hacks to make to work around them. If you're just worried about the practical thing, I think there should be a hack to work around it. Yeah.
Thank you.
Okay. Because it's not just SVD, many of the machine learning methods, I don't know I think at some point you learn kernel methods. There you need a reproducing kernel Hilbert space. So without Hilbert space, nothing happens. Hilbert space, yeah.
Thank you, sir.
Sir, also I think LLE and NLD are also required the same method, non-linear dimensional reduction and those.
Correct. So you need a norm. I mean, see, the point is when you write down dimensionality reduction, there is some error concept, which is measuring distance. So you need a norm. If it does not come in from an inner product, somewhere you will get a miss. Yeah. At least the current proof won't go through. I don't know if there's a way to work around that. It's just that usually I'm not unduly worried about that. Yeah.
Yeah, Manish, you have some doubt, you may ask.
Yes, sir. I was asking in SVD, sigma transpose sigma and sigma transpose, are they same or different?
You can answer that. What is the size of sigma?
Sigma is, I think, sir.
Is it square or rectangular?
It is square, sir.
No. I mean, if A is m cross n, what is size of sigma? Where m is not equal.
So most of the time I solved it using the square matrix.
Square, but if I say A is like having 3 rows and 2 columns,
then sigma should be 2 cross something.
2 cross?
If u is 2 cross 3, then sigma should be 3 cross.
No, what is u? You are writing A is equal to u sigma V transpose. Now u and V are square matrices or not? Let's answer that.
U and V may not be a square matrix.
No, you'll have to go back and read about SVD from scratch, because U and V are orthogonal matrices, they are square matrices. The one which is not square is sigma.
Oh, sir, U and V is necessarily a square matrix.
Yeah, they have to be. Because you're putting eigenvectors. Imagine Q1, whatever U I called as Q1. You're putting M eigenvectors there as columns, and each of these M is a M-dimensional vector. So it's a M cross M matrix. Similarly for Q2. Yeah.
Okay, sir. I will read it again.
Yeah. So please read it. Try doing SVD for a rectangular matrix. Take a 3 cross 2 or 2 cross 3. If you want, I can give it to you right now. Just do it. Yeah.
Yes, sir. Thank you, sir.
Yeah, so any other doubt, please go ahead and ask, or any general feedback, right, sir?
Yeah, anything. We still have 25 minutes. Now, people, if they want to understand some more geometrics, I could not add this lecture, but I can give you some section reference.
Yes, sir. Yes, sir. That would be very helpful because
Okay.
a few geometrical
Whoever want to
things.
understand geometrics of positive definiteness.
Sir, you are on mute.
No, I was not on mute. The host muted me is what it said.
Oh, okay, sorry.
Yeah. Okay, so I'll give you 2 sections that you can look at. I'll quickly share. I was trying to dig into this to find out the sections. Where are bookmarks? What was I doing? Are you able to still see my screen?
Yeah, sir,
Yes.
it's visible.
Okay, so this is linear algebra and its applications book. Something like this should be there in Intro to Linear Algebra. It's just that I have a hard copy of this book. I just teach everything from this book. This is equivalent to the Intro to Linear Algebra in many ways. So here, if you look at ellipsoids in n dimension, this is page section 6.2. Wherever you know this positive definiteness comes up. Okay. You know, when I taught positive definiteness, I taught it from here only with all the examples. Okay. And then this, you know, these conditions, all eigenvalues are positive, those equivalence, all of this, I think at some point I taught in the course. The geometric interpretation is here. Okay. Do you see this section? Okay, so the way to understand this, I'll give you a very simple idea. Maybe I'll spend a few minutes on this, couple of minutes. So if you look at x transpose Ax, right? If A is identity, I get x1 square plus x2 square and all. So that's the, just take the 2-dimensional case. If I have x1 square plus x2 square equals 1, what kind of a thing is it? It's an equation of what kind of an object?
Circle.
It's a circle. Now, if x1 square, if 2x1 square plus 2x2 square equals 1, then what is the difference between that versus x1 square plus x2 square equals 1?
It's a circle with radius square root of 2.
Yeah, that's all. So it passes through different points on the x-axis. That's what he has written. If A equals 4i, then instead of passing through 1, 0, 0, 0, it will pass through half 0, 0, 0. Okay. All right. Now, if I take a diagonal matrix where the diagonal entries are all not same, I'll get, when I write down x transpose Ax, this may be a little fast. I would ask you to go back and read carefully. But if the matrix A is not identity, or if it is not some constant times identity, but if it is still a diagonal matrix, then I get that equation. Okay, in the case of 2-dimensional case, if I write 4x1 square plus x2 square equals 1, what is that? It's not a circle, but what is it? 4x1 square plus x2 square equals 1.
Ellipse.
It's an ellipse. In general case, it's an ellipsoid. In the n-dimensional case, that first one is a sphere and the second one is a ellipsoid. Okay. Understood. That's the generalization about x transpose Ax. Do you understand this much? Okay. Now the next thing that comes about is, this is, if you look at this matrix A, which is either identity or some constant times identity or a diagonal matrix with only positive entries, are these positive definite matrices? Have people forgotten about positive definiteness?
No, sir.
Can you? Okay, positive definiteness. So what can you tell about the eigenvalues of a positive definite matrix?
All are positive.
All are positive.
So this matrix A equals 4, 1, 1 by 9 along the diagonal and 0 elsewhere. Is it positive definite?
Positive definite.
Yes.
Why? Because what are its eigenvalues? There's just staring at
All
it.
positive.
Okay,
So
now
4, 1, 1 by 9.
Okay, now the next question is a positive definite matrix necessarily diagonal?
No.
No. So you can have a matrix like in this example 3, 5, 4, 4, 5. Okay. This is a matrix. If you work out the eigenvalues, you will get that it is positive definite. Okay. Got it?
Yes, sir.
And then if you work out the eigenvalues, you will get lambda 1 equals 1, lambda 2 equals 9. And the corresponding eigenvectors are this. So what is the difference? So here, if you look at the ellipsoid, this ellipsoid, if you look at the axis of this ellipsoid, they are aligned to the coordinate axis. Is that clear? I can't draw. I think I can still draw here. Okay, let's see. So if I have, let me try drawing something. This is so thick. Would I change the thickness?
So we are not audible, I guess.
No, I'm not talking, man. Now.
Okay, sorry.
No, I was trying to adjust the thickness of this pencil. So this is your ellipse. Okay. So the axis of this ellipse are here. They are aligned to the XY axis. Clear?
Yes,
or x1, x2.
Yes.
Okay, but if you look at the ellipse of this person, this matrix 5, 4, 4, 5, the ellipse is here. I can't highlight anything now, but yeah, so this ellipse, so this, look at this one and this one. It's tilted. Got it? So this, look at this and look at this. Got it?
They are orthogonal.
Yeah. Yeah, no, not just orthogonal. These are the axes. So if you go here, this was aligned to the coordinate axis.
Okay, so we are actually rotating the axis along the
yes, we are rotating
major.
it. Yes, you are rotating. That's because some off-diagonal entries came, you got rotation. Okay. The second thing you have to recognize is this X transpose X. You look at this X transpose X, that can be written as, rewritten like this. Now, can you relate this bit? So here there is a 1, that is lambda 1. And here there is a 9, this is lambda 9. And
Major axis is 3, the 3 square, the 9 and 1 are eigenvalues.
Yeah, so the major axis corresponds to 1, the smallest eigenvalue. Okay, so the way to do this is rewrite this X transpose X as a function of eigenvalues and eigenvectors like this. And look at the smallest eigenvalue, the corresponding term, that will be dominant. See, the point is, if you want to make the second one 1, you have to multiply by 1 by 9. That's the point you have. So this generalizes to X transpose X when it is diagonalizable. So if it is diagonalizable, look at this. Then I can write it as this transformation where Y is Q transpose X. So what is this Q doing? Q is orthogonal matrix, right?
It's rotating.
So it won't change the length, but it will rotate. So I can write this as Y transpose lambda Y and I'll get an ellipsoid equation. So that's the geometric interpretation. Got it? This is not very different from what I have been talking here. Okay. And this major axis will be the one which has this one. Okay.
So the way to interpret is then in that case, typically most of the time eigenvectors may not be aligned with the x coordinate or x axis or y axis. If it is at an angle, if you rotate it along the direction of the
correct, yeah,
vector, then you will get the, like very similar to the PCA, you rotate along where the eigenvectors are pointing.
Yeah, so that's where this Q transpose comes in. You can just do a transformation and still look at it as an ellipsoid. Yeah,
that's right. Yeah.
Yeah. And that's so this comes, I mean, this lambda 1 y1 square, it's an ellipsoid equation. But the question now is, which is the major axis? The major axis is related to lambda 1 and not lambda n. Lambda 1 is what it is related to. Okay, the length of the major axis is 1 by square root lambda 1. Okay, so these are things that you can look at. This is the first thing you can look at. You can dig deeper into this. But this, so all of this makes sense when lambdas are all positive. Okay, when are lambdas positive? Hello? For a positive definite matrix. So now do you understand why we started with all this positive definite matrix business?
Yes, sir.
Okay, so geometrically, all of this logic, geometric interpretation makes sense only if lambdas are positive. Otherwise, what is 1 by square root lambda 1 or nothing? I mean, so it is positive definite matrices for which you can talk about this ellipsoid and interpretation like that. Don't get confused and try doing it for any matrix. For positive definite matrices, X transpose AX leads to an ellipsoid equation. Okay. Now, the second thing that you can look at is from a different book. This is a little more involved, but this is a book by, this is a more full-fledged introduction to linear algebra, Karl Mayr. I hope you can remember. Whoever is looking at it, just write down this book name. Okay. Have you taken note? Just search for Karl Mayr linear algebra, you'll get the book. So here there is a section on SVD. Get rid of this. Here, if you come here, this section on SVD, the geometric interpretation is covered here. For me to cover the geometric interpretation, it will take 20 minutes. Unfortunately, I can't do it now, but please look at this section 5.12. Okay. Again, the same logic comes here. And also the second thing that gets covered, if you're truly interested, there's also matrix norm which comes here. But the important thing that gets here is, imagine this part. Look at this. Imagine instead of AX equals B, B was a B tilde. Okay. So if you have some error in measurement of B, all right. So this was B tilde. Okay, I should erase this in circle properly. Then if you go from AX equals B and to AX tilde equals B tilde, then how much does the X change? Does it change drastically? Okay, all of this is related to something to do with SVD. You can answer all of this through SVD. Okay. So this is, how sensitive the solution to a linear system is when I change the coefficients, like from the B, not coefficients, from the this whatever you call this B as. Yeah, A is the coefficient matrix, B is something. Okay, so all of this is related to something about this matrix A, and that can be worked out through SVD. Okay, so I would say just check out this section 5.12. This initial decomposition part I have covered, but I didn't do the geometric part. This is something you can fill on your own. Yeah. Okay. For geometry of SVD, maybe Gilbertstein may have it. I don't know. I studied it here. Okay. This is a good book. If you want to pick up linear algebra better, solve problems from any book, Gilbertstein or Karl Mayr, Horn, Johnson, Hoffman, Kunz, take any book. Because at this point I will stop sharing. You can take questions now. Okay.
Yeah, we have only a few minutes left. Please go ahead with your questions. Or any general feedback, comment, whatever.
Yeah. No questions.
I have a question, general question. I think all these work that we're doing in MLF are essentially building up towards machine learning and MLT and MLP later on. So I guess one thing would be nice is maybe it is like a Math 3 plus Stats 2, right? This is like a preparatory course. So many times, a lot of these things that we are learning, when we start coding and start using real life data through Python, then I think it will start sinking in better. That's generally, I think, is feedback. But yeah, I mean, I think with the videos, the time is limited. It becomes very dense. I think these kind of sessions are very helpful because then we have a chance to interact with you and ask questions.
Yeah, you can clarify. I mean, if you still have questions, we can have one more session.
That will be great, actually, right? So then we refer to the material that you suggested, sir. So we'll go back and read and then maybe have some more better questions.
If you're totally interested in geometrics of this, then yes. But whatever I've taught as part of those videos are good enough for you to dig deeper into. Like in the follow-up courses, whatever comes up, this much knowledge is enough. But if you are a person who is highly interested in geometric viewpoints, then those two things that I said can be checked out. Yeah, those are like add-ons, not really like, yeah, those are add-ons which are specific to individual person's interest. Yeah.
Thank you, sir.
Yeah, anyone else? Anything? So this time we have more people in terms of numbers, and there has been few, I mean, a lot of queries in linear algebra due to mathematical nature of it. So therefore, I am asking everyone to ask doubts. So we are getting this opportunity for very
if there is a topic that they want me to explain, yes, I still have time to do that. Or if there are still a lot of queries pending, if they pile up, then we can have a follow-up session also. I'm fine with it. But you know, we should not be in a situation where we have to keep asking the students for questions. Like the question
sir.
on that side. Yeah.
So anything that you want to share with students, a general motivation kind of?
No, generally, I would say for any math course, I said this before, go and solve problems from Gilbert's fan. Whether you get good marks in this course or not, it does not matter. Your understanding of linear algebra is entirely tied to how well you can solve those problems. If you feel totally lost, then you have to seek help. Yeah. Otherwise, if you are able to solve most of the problems, then it's good. Yeah, then you have a reasonable understanding. So I would say for any math, even probability or the other optimization parts of this course, the only way I would say the best for best results, please solve problems. I mean, no amount of looking through videos will help unless you solve problems. Because you think you have understood something and then I'll give you a matrix and then you try to solve, you get stuck and things like that. Yeah. So if you solve problems, you'll have better experience. It's like ML only, it's meta level in the sense, it's like these problems are like the samples, data points. The more data points you look at, the better model you can fit. Similarly, if more problems you solve, yeah, better you understand.
But there should not be redundancy.
Sorry, what?
I think Yogendra said something.
No, sir. I was just saying there should not be redundancy. There should be orthogonal.
No, which one is? I didn't understand which has to be orthogonal to which one. Yeah.
Significant, I think. Yeah. So, sir, actually, the thing is, we have also been saying them to be patient for courses to come. I mean, we are only building the foundations for the courses to come. The mathematical aspect of is very important, but people are being a little impatient. That's the thing.
No, math requires patience. You'll have to sit calmly and think, shut off social media, shut off everything else, and calmly try solving problems. You cannot be distracted and desperate while solving these problems. Yeah. And that's probably a high level guideline. So you have to go back in time, like those old school pen and paper modes. For solving problems, pen and paper mode is the best. Any other mode would lead to distractions. Like you need to have a sound understanding. Even if you want to code up and interpret results, whatever you do, you need to understand PCA at a good level, SVD at a good level, and things like that. That will come if you are able to solve problems. Because these problems in all these textbooks will test various parts. I mean, various aspects of these algorithms. So it's good to solve.
Yeah. So any further doubt, any comment? Please go ahead. we have few minutes, very few minutes left.
Yeah, if you cannot solve a problem, seek help. That's still fine. Just don't unduly worry. That's it.
So one comment was the questions in the first quiz are really nice. There are certain things which was really nice. One question I remember, usually you are given a matrix, you find the eigenvalue, then find the eigenvector. We went to the exam, we saw, okay, here is the eigenvalue, eigenvector, find the matrix. I mean, it was very interesting. I think you are forced to think fundamentally what is happening. And it was good. Actually, even the learning happened during the exam. Because you thought
but you know, there's only so much you can do with multiple choice. In fact, it's just that's the reason why I've been insisting go solve problems outside. It doesn't see in the end after you graduate from this course, nobody is going to care about your marks. It's only your understanding that you carry. So how well you solve problems is all it comes down to. I mean, some people are very good at multiple choice. They're good at guessing or whatever. But in the end, your understanding is what will carry you forward. So solve problems. They will test your understanding. You'll have to do detailed steps, things like that. Yeah.
Second thing is this course also has a lot of working professional. I'm a working professional. I think there's a good mix of working professionals and students. Some of these Thursday classes we are not able to attend because of work commitment. So weekends are really good. So maybe towards before the end and all that, if we can have another interaction session with you, sir, I think that would be really helpful.
Yeah, there will be a session interaction towards the end. Also, for each part, I think there will be an interaction with the individual. There are 3 instructors for this. I'm handling linear algebra. I believe the other 2 segments also will have some interaction. I think Abhinandan can clarify. But then after that,
Yeah, these sessions are subject to professor's availability. So thanks a lot, sir, for giving us time. I mean, it's a very nice gesture and it helps our students a lot. I mean, the comments that we are seeing that they are getting 10x motivated. That's great. I mean, by one of your sessions.
Sir said stay away from TV and WhatsApp or whatever social media. If
no, while solving problems, because they require you to focus.
Yeah.
Because if you're looking at some matrix, trying to figure eigenvectors, you cannot do multitasking while solving a problem.
Yeah, I agree.
Yeah. Otherwise, just stay glued to the TV or OTT or whatever. And it's not like I'm away from OTT, but it's just separate things. Yeah.
Yeah. So if there is no more questions, I mean, if sir wants to speak something, he can, or otherwise we can close the session.
I am not. There's no vote of thanks. It's just a session where people are supposed to ask questions. If we are done, we are done. That's it.
Okay. So thanks a lot for all of your participation. Thanks a lot, Prashanth sir, for being here and sparing your time.
Yeah, sure. Yeah.
Thank you so much, sir.
Thank you, sir.
Thank you. See you.
Thank you. So we are good to close. Bye.
Thank you, sir.